Hello, ladies and gentlemen. Thank you for coming to our presentation. My name is Ivan Querl, and I'm representing ITMO University and SD Cloud project about cloud computing model. So let me start my presentation from an interesting quote from Mr. Box, who says that essentially all models are wrong, but some of them are useful, which is very important when we're thinking about modeling of any kind. So the brief background, our project is working on the cloud infrastructure for system dynamics modeling. And what is system dynamics? Essentially, system dynamics was established in 1950s. It's more than 60 years old, and this year, as the cloud community celebrates the 60th anniversary of system dynamics. So this is a methodology which allows us to investigate how different dynamic systems are working, how they're evolving, and how can we improve them, and so on. And also, system dynamics found quite a range of applications in different areas, like social areas, economics, different technical systems, and so on. Basically, when we are thinking about modeling and how we do modeling, we can find several important stages we always came through. So first of all, we're analyzing the target system we're going to perform the modeling for. Then we need to identify the modeling parameters and the properties we want to pass to the model or to configure model to use it in the future. So next we need to design a model. So we have to define which particular nodes we have, and we have to identify the relationships between these different nodes and how they interact with each other. Then we're performing a model execution and see the results. When we're analyzing the results, we can look back at the system, target system we are modeling right now, and we can perform different executions with different parameters to figure out which model configuration suits better for this particular situation. But sometimes tuning the parameters is not enough. We can see that, for example, we didn't take into account some relationships, and we go back to the model design and we improve the model design. And if we see that, look like we can change the design of the model, but it will not bring significant benefits in improving the quality of our model, it means that maybe we missed some parameters or properties, and we need to re-identify, revise this part of the model. And so the most expensive part, if we see that different configurations and model structure changes didn't bring required effect, so maybe we were wrong. We were analyzing the systems we're working with. In this case, we need to start from scratch and we analyze the system. So all these aspects are done mostly manually. So we are looking at the system, we're looking at the model, execution results, and we're trying to put this stuff together to figure out what's going on and how well we reflect our real system with our model. If we look at from at a glance, we can see that we're taking information about the model, we're putting it into the about the real system, we're putting it in the model, performing modeling, and so on, and then we're applying our results back. And actually, we have a real brick wall between the model and the system which we're trying to model. And to make our models better and to make a feedback loop we have between the model and the real system smaller and shorter, we need to introduce a kind of interaction between the real system and the model which we are currently using. So what are the key issues with the existing paradigm? First, the system, we have several assumptions which we are always following. First is that we're assuming that the system was stable and it was behaving according to the model while we were analyzing its future without our model. In real life, anything may happen. So, for example, we take some state of the system and we're starting modeling from this point. And in our model results, we see that the system will go in direction A. But while we were modeling, something happens in the real system which was completely unexpected. For example, if we are modeling the traffic system, maybe just car breaks down in some place. We can't predict this situation in our model because it's completely random event, but it will just require complete reevaluation of the system, remodeling with new kind of input data. The second assumption is that the system will behave according to our model, and our management decisions will lead the system to the target state. So if we make a model and we perform execution and we see that our model really well works with our system, so we may assume that, okay, so we can do the planning with our model and we can predict the future and it will be really like this with a very high chance. But on practice, again, anything may happen in the future. And if we saw in our model that in 2 weeks we came to some state with our system, it doesn't mean that we really be there. So most probably, with high chance, we can get there. But how can we handle unexpected things in the future? And the third thing is the system will endlessly comply with our model. Especially when we're talking about dynamic systems and system dynamics modeling, we're dealing with evolving systems. So it means that these systems are changing over time. They are not changing according to what we have in the model. We have element of evolution and degradation of different model parts. For example, after long use, some technical parts may start to behave differently than they were, and it's extremely hard to predict such things in the real model. So, from this particular list of issues, we can define a set of goals we want to achieve. And so we have a problem, and we have to deal with it. So, let's see what's the goal which we're trying to achieve. So our goal is to design a modeling approach that will stay on the edge of the pure classical modeling and in the same time will be really in sync with in a state perspective with the real systems we are working on. And to achieve this goal, we need to reduce the level of uncertainty between running model and really working system. So let's look how we're trying to solve this. Essentially, system dynamics model consists of two major important parts. Is stocks. It's a term for any entity that accumulates or depletes over time, and the flow. It's the rate of a change in a stock. So, for example, in this particular model, we are talking about the new product adoption, and so we have two states. We have potential adopters, and we have adopters who already just moved to our product. And we have some flow which transfer people from potential adopters to new adopters. If we will look at this from the modeling perspective, what is system dynamics model execution? It's computation of the model frames over time. So we're making a next model step, and we evaluate state of all stocks by computing all the flows and all other parts of the model. So we have a model and we have a real system. And when we compute the model, we are moving from one state to another. In parallel with this, our real system for which we are making a model is also living its own life. So it's also moving from one state to another. And to take all this, both these guys in sync, what we need to do is we need to somehow to perform a state transfer. So we need to somehow let the model know in which real actual state our system is. And to do this, we need to do the state transfer. So especially it's very well applied to the IoT systems, because IoT system generates tons of messages describing different parameters of the system, so it's very easy to record the state of the system, and it's very easy to deliver these state changes of the real system to the system which we are trying to model, to our model. What is the state change? Let's say we have a model that's, if it's just a pure model, it's going from the states S1, S2, S3, S4, and S5. So this is a kind of set of time frames for the model. But if we applying the state changes according to what's happening with the real system, maybe something wrong became at the model at the time frame between S1 and S2. If we will apply the state change, we will see that we can shift the model from S2 to S2 asterisk. And it means that future model execution will start from this particular place and go this path, not the upper one. The same happening between S3 asterisk and S4. And we're also changing the way how model is executing. And it allows us to make model much closer to the real system. But not only, but this approach can be not applied to just completely replicate the system state to the model state. Another use case so when we're analyzing the state changes, we can see that model may behave differently from the real system, and this information is very important in real time. For example, on this chart we can see that the red line is the model and the black line is state of the real system, so for one of the stocks. Here we can see that model is really well describing what's happening with the system. We see some changes, some deltas, and this is okay because the red line is computed according to the model information, and model never contains all possible information about the system, and that is why there is some data which is actually very close to the main line, and we see that our model describes the system very well. On the next chart, we can see that our system behaves really different comparing to the model. So it means that there are important factors in the real system which are not counted in a model. So as longer we will run our model, as bigger this dip will be. So here in this case, the state transfer which we described, which we introduced in the SD Cloud, may just shift model execution closer to the real system. So for example, if we are not able to describe all possible forces present in the real system, we can rely on putting the data and just tuning the model statically based on the real system information. But also we can get even more interesting information. For example, on the next chart, we can see that in the beginning, until this moment, so the system and the model were really close. So it means that, wow, we have a really good model and we can work with this, we can rely on the results of this model and the execution results. But after some moment, for example, the step number 15, we see that the difference appears. It means that something happens in the system which is what is not expected by the model. It means that some new force appeared, or maybe something became broken, or some external force starts affecting the system, and so on. So when we're working in the real time and we, for example, monitoring a complicated technical system, it means that we need to take attention to our system because something changed and we need to take care of it properly. But monitoring the system completely is not the only option we can benefit using the continuous modeling approach. So let's say we have some technical system. It's complicated, it has a lot of nodes and a lot of internal relationships between these components, and we want to extend this system with something else. When we want to design a new system, first thing we can do is try to build a model of the system. And we're building a model. It's also just since it's kind of atomic part which can be added to this existing system, it has its own causal loops diagram, it has its stalks and flows, and we want to figure out how this system we're working on is working with the real data from real system. In this case, we can perform a kind of integration of the real world and the model. So in this use case, we are not just putting the state of the real system inside the model and correcting the model behavior and model current state. We're just adding new information to the model. So instead of taking some table inputs, which we take from historical data or so on, we can inject the real behavior of existing part of the system into the model execution. So this is essentially it about our approach. Thank you very much for your attention and the questions.